Somebody's done the timer. So I'll kick off then. I'm Simon Riggs. I'm going to talk about Postgres partitioning. I'm going to talk about it for 49 minutes and 16 seconds. So I hope you've all had your breakfast. The lights in here are so bright that I can't actually see people at the back. So if you stick up your hand for a question, I really won't see. So just shout out something. Okay, so what are we going to talk about? Well, partitioning is splitting big tables up into multiple partitions, and that's the topic, but obviously we need to understand why we would want to do that. And I'm also going to explain a few other thoughts along the lines of when you would want to do that, how you would want to do that, and also talk a little bit about some credits for the people that made this all happen within Postgres. So the why of it really starts with an understanding of the problem around partitioning. So partitioning is really about solving problems within very large databases. Obviously, some people think very large means above 100K, and you know, I guess they're right if that's what they think, but really we're talking about challenges above 100 gigabytes, which isn't that large these days, and so it's still very applicable. So the idea is that sequential scans take a long time, indexes are impractical, and we have difficulty removing older data. So that gives us an opportunity around data organization. Because the way that the database heap works, we just stick the data in any old place in the tables without really thinking about it too much, which is difficult when you want to remove the data later. So if the data is properly organized, it's easier to remove, and it's also easier to add. And you can also use that structure within the queries themselves. So that gives you a number of solutions. If the data is organized naturally over time, for example, an ascending order ID or a monotonically increasing timestamp, then you can see that the data at one end of the table is going to be old and the data at the other end of the table is going to be relatively new. And you can actually use that fact to improve query performance. And that's actually what we already do with something called a BRIN index. So whenever people talk about partitioning, I always make sure to also talk about the BRIN index, because although it's an index, it's termed an index within Postgres, it does actually, it's designed specifically to solve the same problems that partitioning does. And the original project that we created that became BRIN indexes was actually called auto-partitioning. That's what we were trying to achieve. Sometimes you actually want to force the way that the data is organized, and that's where partitioning comes in, where we actually explicitly say which data needs to go in which place. So we end up with the main use case for partitioning in VLDB is what we call rolling data maintenance. So we remove old data by dropping the old partitions, and we add the latest data either via bulk load via copy or just a stream of inserts in at the other end of the table. And also we want to optimize access to data in that typically we find that a lot of data is hot, meaning it's accessed frequently, and other parts of the data tend to be accessed less frequently. So you end up with a sort of Poisson distribution of access to the most recent data. So that gives you a case where you really want to optimize most queries for access to a small subset of the data, whereas you actually want to allow all queries to potentially have access to any data. Now, if you do that, that has a number of advantages, because it means that we can not only increase the scan performance, but it means we avoid churning through the cache as well, which has a significant effect on performance. So partitioning has got some really beneficial outcomes if you use it, but that doesn't mean that you should just use it all the time without any thought. It's a solution to a problem. So you've got to make sure that you've got that problem already, or you're going to have that problem, because otherwise it's going to be a lot of work and a lot of pain for no real benefit. So please be careful. I sometimes speak to people that say they're going to use partitioning, and when I ask what for, they kind of think that's a strange question. So really sort of make sure that you're looking at what problem you're trying to solve. So my summary of partitioning, you can listen to this slide and go and have a coffee if you want, because this is really where I summarize where we are. Postgres 10 featured declarative partitioning. At the time, it was mostly syntax only. It worked for business intelligence queries, but we've been improving that over the last couple of years. We've implemented, if you look at the release notes, there's 23 specific features related to partitioning in Postgres 11 and Postgres 12. And if you look at the maintenance releases, you'll see that there's at least 27 bugs fixed on partitioning over the last year alone. So what that tells you is a lot of people using it, the feature set has expanded, and the status of partitioning as of Postgres 12 is that it almost works in all of the important cases and is properly optimized. So it will be fully usable for OLTP in Postgres 12. Now, you might have a right to say, so why didn't you tell me when you introduced partitioning in Postgres 10 that it didn't quite work right for OLTP yet? I guess it would have been nice if that had been added to the release notes, but it wasn't. So now there's a whole load of other features being added at the moment to Postgres that is kind of interrelated with partitioning, and the main goal of those features is sharding. Now we do not have the sharding feature set solved within Postgres 12, so I wanted to make a clear distinction between partitioning on a single node and sharding across multiple nodes is not a solved problem. Okay, so I don't want to confuse you. I'm not going to talk about sharding, and if I mention the word BDR here, that will be the only mention in this talk of sort of multi-node solution space. Okay, so I am just going to talk about PostgreSQL and partitioning on a single node. So the development of partitioning is something that I personally have tracked over more than a dozen years within Postgres. I wrote the original feature for constraint exclusion in Postgres 8.1, and it took us about 6 weeks for me to write it, and then Tom Lane to completely rewrite every line of my code before he accepted it. But that, as I say, it took about 6 weeks, and it was always our intention to improve on that feature set. And unfortunately, it took a rather long period of time to get there. People submitted a patch for partitioning that would work with rules, and I had to point out that that wouldn't work because copy isn't supported by rules. So it was rewritten again, and this time, the next time they rewrote it using triggers, and that doesn't work either. So unfortunately, people getting a bit frustrated with me at this point and say, why don't you tell us how you should write it? And so we did. We discussed how the declarative partitioning needed to work. We discussed the way that inserts needed to work. And so when Postgres 10 came along, we actually had declarative partitioning, working as a primary feature within the core server, and it did perform, or it does perform, constraint exclusion. It eliminates partitions that don't need to be scanned. And so it's actually useful for business intelligence performance. But at that point, it didn't do some of the things we needed for OLTP. So in Postgres 11, we added essential features like the ability to create a primary key on a partition table, the ability to have triggers, which then allows you to have foreign keys on the table. And then in Postgres 12, we've added significant partitioning performance improvements that makes OLTP possible. So all of this work, I mentioned my contribution. Nick Hill was one of the people that submitted the earlier rejected patches, so I've just mentioned him for historical note. The recent work on partitioning has been championed mostly by Amit Langote and committed by Alvaro Herrera, who's written most of the things like primary keys for partition tables and such like. And you'll also see another name that you might not recognize, but David Rowley has been intimately involved in the performance aspects of this, especially the optimizer changes, and he's really been elected a committer as a result of the quality of his contribution. So that's a very good step forward. But I could probably add about a dozen names to this slide in terms of people that added individual features as part of this project. So it really has been a multi-company, multi-year effort to get partitioning into core in the way that it is now. So what exactly have we put into Postgres? Well, it turns out that there's actually many different approaches to the challenges I laid out before, which is basically how do you use the organization of the data itself as a way of improving performance. So if you look at things like the awk format, the awk data format, data file format contains some intelligent metadata within the file system itself, and that can actually be used to implement partitioning approaches, and other open source tools do use that. There's also the using the concept of metadata within an index, and that's what we do with the Brin. Then another approach is to get the partition metadata within the catalog of the database, and I've mentioned the word hypertable there because you'll see if you speak to the Citus guys or the Timescale guys, you'll see that they use that hypertable approach. Now, personally, I think that's a reasonable and valid approach. I don't see anything wrong with it. The only issue was it wasn't in core. So what we've been trying to do is get this functionality direct within core Postgres. The debate is, of course, what's the best way to do that? For example, in Oracle and other systems, partitions aren't tables, but in the implementation that we've put into Postgres, partitions are themselves tables as well, which can sometimes be a little bit confusing because a partitioned table does not itself contain any data. It is composed of partitions which are tables. Okay, so if you're coming from an Oracle background, that can be a little confusing. But just to say that there's actually quite a lot of different ways of implementing the partitioning concept within the database literature and in other databases. So it shouldn't really be a surprise if I tell you that partitioning is not part of the SQL standard. And neither, for example, are indexes part of the SQL standard because it's an implementation detail, okay? So we have had to add things to create table and alter table which are non-standard, and they're very specific to the Postgres implementation. Now that's a little bit difficult because the phrase partition by is already within the SQL standard, but we've completely changed its meaning for the PostgreSQL implementation. So you're thinking, just give us an example, for God's sake. So here I go. So if we've got a table called measurement that is going to take a load of measurements for a particular device, the measurement is taken at a particular time, and there's a load of stuff that, for Andrew's benefit, is in JSON-B, but obviously it could be any type of data at all. And for my benefit, I've added a Brin index just to show how easy that is. And then if you want to implement partitioning, all you need to do on the create table statement is add the phrase partition by, and then you specify the type of partitioning you want, which in this case is a range partitioning, and we specify the column that contains the ranges of values that we're looking for, which is the log TS or log timestamp. That's what it means to me, column. And then that's all we do on the create table. The downside here is that then we need to create multiple subtables using this kind of syntax where we actually give the subtable a name. We mention that it's a partition of measurement, and then we specify a range of values that are known as the partition bounds. So we're saying from X to Y. Now, if it isn't clear already, the partition bounds must be unique, so they can't overlap any existing partition. So that's by definition, there's no overlap. If you go back to the way that inheritance worked, inheritance and constraint exclusion work completely differently, and you could have overlapping bounds on your tables, which was quite confusing. So it's an important aspect of the implementation that the partitions do not overlap. And then, depending on how many partitions you want, you can just create a number of subtables. Now, in most tests you perform, you'll be adding like 2 or 3 or 4 partitions. But in production, you may want to have hundreds or potentially thousands of subtables within your partitioning scheme. And what I'm going to do for the rest of the presentation is talk about aspects of that and considerations that you need to think about. So the partition types that we implement are range, which gives you a range of values. So you can have a range of timestamps, you could have a range of integers, depending on how you're using it. Now for me, range partitioning is the key use case for partitioning. The other ones are they exist and they're a little bit interesting, but for me, range partitioning is like 95 to 99% of the partitioning use case. A lot of time that will be based on timestamp, and so you end up, that's why I've used the example of measurement, because that then is the type of use case around the Internet of Things. Now, you can implement list-based partitioning if your lists are based on numbers, but if the things that you would like to segregate are like text strings, then the only way to do that is with list partitioning. So that allows you to have a partition for the United States and another partition for the UK and that kind of thing, which obviously gives you the problem of what do you do with the EU partition should some data in there need to be moved to another partition, but we'll talk about that later. There is, of course, also the hash partitioning type, which basically effectively just randomly puts data into to different partitions. And it's quite difficult to see how that can be useful outside of the context of sharding. So I'm not going to talk at all about hash-based partitioning in the rest of this talk. So just so that we are clear about what we're talking about, I've got some pictures. So the idea here is that we've got a table called time, and we're splitting the table down into multiple subtables. Now there's no limit to the number of subtables that you can have, but they must all have unique partition bounds within them. So this is an example of a range partition where we have a time-based partitioning scheme where we just add new partitions as we decide to. What's interesting about the implementation we have with Postgres is it's possible to have multiple level partitioning. Now that is not limited to just 2 levels. It can actually be nested quite a long way if you would like it to be. But most people see 2 levels as a potentially interesting use case in that in the example I had about devices, you might, for example, have all of your devices or a specific partition per device, or maybe all the devices in a particular region in one table, and then time ranges within that. Okay, so it's possible to end up with multiple levels of partitioning. Now that doesn't really cause any difficulty apart from the confusion of the DBA with regard to the large complexity and number of partitions. But if you've got a handle on that, then it's not a problem. So what does the syntax look like to manipulate it? Well, I mentioned that we can add a partition to the table by saying create table partition of, but we can also just simply drop that table as a way of removing it from the partitioned table. Another approach is to actually alter the table and attach the partition. So that doesn't create the table, and the detach doesn't drop the table, it just moves it under the partition table or back out again, okay? So the attach, detach syntax is not the same thing as create and drop, okay? Just to be clear on that. So those commands are fairly easy to use. You can script them. I believe there are some tools that you can get to generate partition syntax for you, and I believe that in the future there will be automatic partitioning within Postgres. We just haven't written it yet.
Simon, just a quick question on that. When we drop a partition, does it require an exclusive lock on the parent table?
Thank you. That's my next slide. Excellent. I love it when that happens. So, yeah, the thing that you have to think about with the scheme that we've chosen is that the partitions are full-strength database objects that can be queried individually, and as a result, you have to consider what the locking implications are when you perform certain actions. So in Postgres 12, we managed to get a patch through that allowed share update exclusive lock to be taken on a table. Now that blocks all other DDL. It also blocks DML, but it does allow you to keep doing selects while that runs. Now that's a very important change, but that's only in Postgres 12. So Postgres 10 and 11 takes a full access exclusive lock on the parent table, not just on the partition, okay? Obviously, if you do create table partition of, it's gonna lock the partition itself, right? That's clear. What I'm talking about is the locking that happens on the parent. Now, in Postgres 12, we still haven't yet worked out how to drop or detach without taking a full access exclusive lock. So if you're looking for like exactly when you would drop your partitions, you need to do that with some care. You can't just create a new partition at the same time as you drop an old one, because the drop will have different locking effects to the create. So that's important. One of the gotchas that comes out of that is that Postgres 11 added a feature to allow you to have a default partition that basically didn't have any partition bounds. Now that sounds like a really cool feature, apart from every time you add a new partition, it has to scan all the data in the default partition to see if some of that data ought to go in the new partition, okay? So it does a file scan of the default partition. So if the default partition is big, that DDL is going to run for a long time, and remember it's running with an access exclusive lock, so it's going to lock out your whole system for however long it takes. So basically, as far as I can see, default partitions are a really bad idea. So I'd rather you heard it from me now, and if you think you know what you're doing, go for it. But I'd rather say that to you now than have you go into production and have your system locked out for 20 minutes while it scans the default partition. Unfortunately, we've got a couple of features in Postgres 12 that interact badly, and that we've added some code that allows you to avoid sorting if the partitions are referenced in order. So for example, if you do a select statement order by timestamp, then it can scan the partitions in time order, okay? And therefore avoid certain aspects of data sorting. Now that's great, but there's also another feature that allows you to use expressions as partition bounds. So you might be tempted to have a partition bound that says I'll extract the month from a particular timestamp, and I'll say this partition can be the month of March. Now, if I do that, the extract command doesn't sort. So unfortunately, the optimizer doesn't yet know that if you extract March from a timestamp, then that comes after the extract of February, okay? So if you use functions or expressions as bounds, it can actually interfere with some of your optimizations. So if you're using time range partitioning, please use precise timestamp values, constants, so that you know what is going to happen on the partition bounds. So with that said, I'll talk a little bit about partitioning performance for OLTP. That's what a lot of people think partitioning was for. So that's the thing that we really need to make work. So the goal here is to make all of the operations on a partition table cost the same, no matter how many partitions you've got. So that's an algorithmic complexity of O1, or OK, as I call it. Now that's a challenge in Postgres, because unfortunately the code path for insert is different to the code path for update and delete, which is different to the code path for select. So we've had to implement this 3 times in order to get it to work within Postgres. That's one of the reasons it's taken so long. And it's also one of the reasons why Postgres 10 didn't solve the problem at all. We also want to improve the speed of copy when we're inserting into multiple partitions. So what we've done over the last couple of years is write a load of patches, submit them to core to improve these performance. So some of you will have seen these graphs before because I had them last year. But at those points, we didn't necessarily have them committed to Postgres core. So you can see where we were in Postgres 10 has been drastically improved. The partition performance has increased significantly, but there is still a slight gap at the top between the performance into a single table as against a partitioned table. Obviously, we're trying to reduce that as small as possible, but we haven't got it to 0. Along the way, we've had to tune quite a few different things. For example, high number of tables with high numbers of columns didn't work very well with partition tables, so we had to tune that as well. But what we finally got to was the case where we removed all of the reasons why partitioning with lots of partitions was slow. And we did all of our testing around this particular number of 10,000 partitions. Now, that's not to say that having 10,000 partitions is a recommendation. It's just that we know that some use cases, especially in like very, very large databases, where people might have daily data and then further sub-partitioned within that, actually achieving 10,000 partitions isn't unbelievable. So I've seen there are a lot of people that want to have 10,000 partitions. So originally in Postgres 10, you'll see the 3 columns on the left represent the unpatched or the Postgres 10 performance. And I say 3 columns because there is a green column on the left. It's just not very tall. And that was a fairly small number of transactions per second. So that's how bad things were, unfortunately. But after a lot of work, David Rowley managed to sort of like keep kicking down the doors until we got to the point where patched, we could actually make the performance quite close to the non-partitioned case.
When you say patched, this is 12.
Yeah, so with regard to the way that we develop the patches and we put them in working form into second quadrant Postgres about 18 months ahead of their availability in core Postgres. So all of the work's been submitted, but it wasn't in a working form at the time that we did this, not as in a working form in core. Yeah. But so the reason I'm showing this now is this is the current state of Postgres 12, okay, which hopefully is going to be released in the next few weeks, but we'll see about that. So we did also work on a copy into tables with 10,000 partitions. What you should learn from these graphs is there is a slight performance advantage in if you do the data load direct into a particular partition rather than into the top level partition table. It's a slight advantage. It's not really worth gunning for if it's complex to do. But as you can see, the gain we've made is really quite dramatic over Postgres 10. So where do we get to then? So Postgres 11, sorry, this is Postgres 12. So when we're loading data into a very large table, what we wanted to check was that the load speed didn't go down over time. And so what this graph shows is where we took a batch of 10,000 rows and we inserted it into the table 400,000 times, okay? So that at the end of all of this, we had a table with 4 billion rows in it, okay? And if you look at this graph, it shows that there's just 0 degradation over time as the table grows. If you put a B tree on there, there's a very slight degradation over time. Now, the reason that I wanted to investigate this particular thing is that Timescale had made some claims that Postgres performance deteriorated over time. And we have been kind of trying to find what the problem was, and we haven't actually been able to recreate the results that show that there was a degradation over time. So my next slides do compare the performance of Postgres against the performance of Timescale. I could also have compared the performance against second quadrant Postgres. I could have compared it against Citus, that kind of thing. But specifically what we were looking for was, is there a degradation as earlier results have been shown? And if there's not, then what's going on? But if there is, let's find it and let's improve it, okay? So that's why we're comparing specifically against Timescale in these graphs. So if you look at this particular graph, you'll see that the Postgres performance that we have here is showing that timescale performance is about 226,000 rows per second, and depending on whether you have monthly or weekly partitions, which is the middle set of numbers, or whether you're just having an unpartitioned table, then you get different speeds out of the system. Okay, so that is showing that in all those cases we get pretty linear performance. There's a little bit of a glitch at the end there, but I'm not sure what that is, and it doesn't really seem to represent anything. I think it's just a testing blip, but I don't really have any evidence otherwise. So what we've then done is taken those results and sort them so that you can see how frequently any outliers exist. Okay, so this is not performance over time, this is all the results sorted by speed. So you can see that there's a couple on the left that went fast, mostly roughly the same speed, and then there's a very small number of outliers that in all of the different systems where the performance drops for that time period or that batch only. So from that I can say that Timescale and Postgres are acting completely the same, and that there are some times when performance drops, and I would guess that that's associated with sort of overload around checkpoint. So let's look then at some other performance results. These were performed by a Dutch guy, so they're not my results, they're not Timescale results, they're independently commissioned results. And you can see that in this we have the graph on the left shows what the performance is on a select query. You can see that on the blue one, which is Postgres 11, as we increase the number of partitions up to the thousands, the performance does degrade as the number of performance increases. Whereas in Postgres 12, which is the green line, you can see that the performance is essentially static with the number of partitions. Okay, so hence the graph on the left is select, the graph on the right is insert performance as well, and from that you can see that partitioning becomes usable in the common OLTP operations with large numbers of partitions in Postgres 12. So it's fully usable for production systems. Fully usable apart from some gotchas that you need to understand. Now, why am I claiming that Postgres 12 is okay to use if there are some graphs showing, well, it doesn't scale and it does suck when you have large numbers of partitions? Well, that's because the types of query that do not scale well with numbers of partitions are the ones that where we're not able to apply partitioning effectively to those cases. Now, what you need to understand at this stage is that there are issues related to particular functions as to whether a function is stable or volatile or immutable. And depending on the categorization of those types of function, it will allow the function to be assessed at planning time or at execution time, or not assessed at all until the last minute. So if you have a volatile function, it will be, it can cause performance problems. So if you're creating your own functions, you need to look at whether that function should be marked volatile, stable, or immutable. And that's especially true when you're using partitioning. You also need to understand the difference between plan time and execution time partition removal, okay? Now, I could probably talk for another half an hour just on those topics. So because these topics are not specifically common, it's not just a function of partitioning, I'm not going to go into those in detail here, okay? But just to say, if you know what you're doing and you write your queries carefully, as I would expect you to do on a multi-terabyte server, then you will enjoy scalable performance. If you are incautious as the way you write things, then your performance will suck. But that was kind of true already, even before partitioning came along. But obviously what I'm trying to persuade you is, if you use partitioning, that is not the only thing you will have to think about, okay? You need to implement partitioning and then also take the same level of care that you would have had to do anyway, okay? And unfortunately, that does mean that you need to understand how timestamp data types work and how casts work between different types of timestamps. These points may be rather irritating to you as DBAs and developers, but there's no real substitute for understanding how these things work, okay? If you don't understand how they work, you're just going to walk smack into a brick wall that's waiting for you. And so if you don't know what I'm talking about, please look up the manual. I could talk for half an hour on either of those two subjects, okay, and still only just get it across to you. So I apologize if I'm kind of saying, oh, like there's a problem and then I'm not explaining it, but really it's complex enough. I don't have time to do it given my 6.75 minutes remaining. So what are my takeaways from this? So Timescale and Citus had working partitioning via the use of hypertables, working within their extensions for at least the last 3 years, okay? So I take that as a very good sign that the Postgres ecosystem is healthy, it's working. The technology around extensions is having a positive effect on the Postgres community, because we've been able to bring a solution into the arena quicker than we've been able to do in core. But we do now have those things in core. So the approach that we took with the patches that we had was that we wrote the patches, we made them available in second quadrant Postgres, but we also published them to core. So second quadrant Postgres is a fork of Postgres. It's just kind of like an advanced fork where almost all of the features are being put back into core Postgres ahead of time. So am I pushing second quadrant Postgres on you? No, okay? It's actually the same price as normal Postgres support. So if you want it, it's there. If you don't want it, we're cool. What is important is that we understand that Postgres is moving forwards, and core Postgres offers you the stability you need for your applications. But sometimes you will need other extensions or forks of Postgres in order to solve specific problems. Okay, and the beauty of the ecosystem that we're in is that these options exist for you. So, and the next thoughts really around that is that if you don't see something in core Postgres that you like, if you want it changed, you can speak to one of the vendors to get them to add it to their product, or you can hire people to write new features for Postgres, which is one of the things Second Quadrant does. So that is all the beauty of the ecosystem, okay? But obviously, if you are using forks or extensions, please make sure to check whether the features that you are being told about don't already exist in core or will do fairly shortly, okay? Because I think that's a very important point. So while I'm encouraging the thought that extensions and forks allow you to have solutions, immediate solutions to your problems, obviously in the longer term, we all are interested in seeing things go into core Postgres. So, Postgres 12, where is it? Well, I see a kind of group of people all sitting at the back there who are likely responsible for these things. No, I mean, look, we're all responsible for when Postgres 12 comes out, okay? Who has taken the time to download the beta, investigate their use cases, and report bugs? Who's done that, okay? So when Postgres 12 is late, you'll know who was responsible, right? So Postgres 12 hopefully is going to appear soon. It does have a release management team. It's been actively worked on in beta for months, so it should be in a good position to release. The long beta period allows us to synchronize the release of a lot of other sub-projects. For example, the usual suspects of Rep Manager, Barman, PG Logical, etc., are all synchronized with Postgres 12. So when it releases, you'll have the full ecosystem, not just the core server. And of course, it's supported by Second Quadrant and many other vendors that you see here today. So there's another shipment of books in. Some of the things I've talked about today are quite well described in the latest cookbook, and I assume that there will be further versions of the cookbook as well. So, given that I have 90 seconds remaining, just to say, I hope that's been a useful introduction to what you can do with partitioning. I hope that you picked up actually how simple the syntax is for partitioning, and that it is relatively easy to use. We will further extend partitioning in later versions to be even more easy to use. But the things that will remain as challenges for you on a very large database is to take a lot of care with your queries to make sure that they are correctly picking up the full advantages of partitioning. And that's not really any different to if you create an index, you need to be careful that your queries use the index, okay? So that's not really a change in the way that we think about things, but it is something that you need to take care of. Anyway, so thank you for listening to me. If you want to talk to us some more, Second Quadrant are over there, or if you're motivated to talk to other vendors, then go and talk to them as well. So last day of the conference, I hope you enjoy it, and thank you very much.